So here I'm going to look at an example where we are going to use quantifiers. So here we rewrite the following statements using quantifiers, determine the truth value of each statement. If the statement is false, provide a counterexample. If the statement is true, provide a short proof. So the first one we have for every real x squared is greater than x. We need to first write in the statement using quantifiers. So because it says for every real, it means for all x. X is an element of the real numbers because it says real. So it's an element of real. And then we have x squared is greater than x. Now because x squared is greater than x, and it says it's for all values of x, we need to determine, is this true or false? Now this is false because I can find more than one example, and you just need to find one example that shows that it's false. So if I choose x equal 0, and that is my counterexample, 0 squared is not greater than 0. That is not true. We could choose, say, x is equal to a half. A half square, which is a quarter, is not greater than a half. So this statement is definitely false. So for you to note that it's false, you need to be able to find an example that proves that this is incorrect. Because they're saying for all x, you'll have x squared greater than x. That's not true because x equals 0 shows that it doesn't work, and x equal half shows that it doesn't work. For part 2, for some real x squared is greater than x. For some, so there exists some x values that's an element of the real number where we have x squared is greater than x. Now, is this true or false? That's true. Because it says some, it means we would pick some numbers that will satisfy. Now, proving it, since it says provide a short proof that we can use is square rooting both sides. If I square root both sides, I will have this as x is greater than root x. And looking at this, where x is greater than root x, it's still true. Because if x is equal to, say, 5, when I put 5 here, the square root of 5 will be smaller. If I choose x to be, say, 7, when I root it, it's going to be smaller. So in this case, my answer is true. For part 3, it says for every real x, for every real y, x squared is less than y plus 1. Is this true or false? First, let's write the quantifier. This is a nested quantifier. It says for all x and y is an element of R. It's R because it says real. We have x squared is less than y plus 1. Or we could have it for all x, an element of R, and for all y, an element of R, we have x squared is less than y plus 1. Both of these are the same thing. Now, is this true or false? This will be false because it's saying for every real number that we have. So for every real number that you pick for x, we have all the real number for y that when you put them together in this expression that we have here, it will satisfy. And that's not correct. Because if I choose x to be 6 and y to be 3, I just use an counterexample. That sure is not correct because I'll have 6 squared. It is not less than 3 plus 1. So, therefore, this statement is false. We have for every real x. So let's start. For all x, an element of R. And we have for every real y. So for all y, an element of R. We have x squared plus y squared equal 9. Is this true or false? And just remember, we could have it as for all x, comma y, an element of R. Then we have x squared plus y squared equal 9. Now, this is false because it's saying for all x and y, x squared plus y squared is equal to 9. And an example, if I choose x to be 0 and y to be 0, because it says for all x and y, so it doesn't matter which number you choose. And 0 squared plus 0 squared is not equal to 9. So that's why it is false. Now the final one, which I'll do here, it says for every x, every real x, so for all x, an element of R, and for some real value of y, so there exists some real value of y, there exists some y, an element of R, we have x squared is less than y plus 1. Let me go ahead and rewrite this. So we have x squared is less than y plus 1. Now, is this true or false? It's true. And it's true because it says for all x, there exists some y. This is a nested quantifier. So it means if I pick x to be 2, then I'm going to choose a y so that it's satisfied. So if x is 2, I could choose y to be 5. So in this case, I would have 2 squared, which is 4, and 5 plus 1 is 6. Proving this, we can prove it by saying that let y, we can prove it by saying let y equal x squared. Why? Because given this condition, this side has to be greater than x squared. So the smallest number y can be is x squared. It cannot be smaller than x squared. So I replace y to be x squared. So therefore I'll have x squared is less than x squared plus 1. So in this case, because I let y to be x squared, no matter what is x, because this is x squared, it's always going to be a greater than it by 1. So in other words, if I say let x equal 5, then that means I'll have a 5 square here, which is 25. But over here, because I said let y equal x squared, then it's going to be 25 plus 1 over this side. So that means if I had let x to be 4, then 4 squared is 16, then this side would be 16 plus 1. So in other words, we choose a number that it is going to make it greater than x squared. So if I choose any value, which in this case, whatever we choose for x, we know it's going to be greater because we choose y to be x squared. Thanks for watching. Don't forget to like and subscribe to my channel.